Okay, so we'll finish up chapter 5. We've really got like 3 minutes left of only the stuff that we need to talk through, I should say. And then we'll move on to chapter 6. And I think we already said that chapter 6 is what? Not on this upcoming exam, right? But the next one? Yes?
I thought we said 4, 5, 6.
Yeah, I think that's what we originally, but remember we got a little bit behind on the first exam there, so that's fine. We've got the rest of chapter 3, 4, and 5, and there's plenty of information in that one too. So besides, we wouldn't be able to get that far into chapter 6 anyway, and you guys will, the beginning part of chapter 6 is a little bit of a tricky math part anyway, so we'll kind of push that off. But it's all right. So anyway, chapter 5, the last part that we were dealing with was Hess's Law. And Hess's Law was just a giant exercise in bookkeeping, just to make sure that we can figure out the enthalpy of a reaction based off of intermediate reactions or subsequent reactions or other components to it, right? And this is I think it's pretty much exactly what you guys did in lab this week, right? You guys were dissolving some things, you guys were measuring the changes in temperature, right? Using the science cups, and then you guys had some delta H's to calculate from there, right? Okay, it's the same idea here, right? Hess's Law is just kind of a added component to that. Again, there might be this impression that I'm like withholding information from you guys, like if only they knew the secrets that I did, then everything would be easy. It's not, right? You just have to work through these Hess's Law problems just a couple times, right? The idea behind it, though, is that we can manipulate individual reactions. If I flip a reaction, if I reverse a reaction, I have to reverse the enthalpy of it, right? If I double a reaction, I have to double the enthalpy. That's the idea to keep in mind with this, okay? So go through, there's a couple of great examples in the back of the chapter there. You guys are aware for the exam, not that I've written it yet, but for the exam, I just pull stuff from the book, right? So it'd be a great idea to work the stuff at the back of the book. And your first response would be, well, geez, Dr. H, I don't have all the answers to the book, right? If only you knew somebody who might have those, right? And it's Jill. So, I don't know, she might, I don't know, right? But anyway, if you guys, you work through a problem in the book, you're like, I don't know if I got this right, I've got the answer keys, I can't post the answer keys for you guys, right, because that'd be a copyright issue, but if you come by my office, you're welcome to borrow the teacher's edition, so to speak, and you guys can look through that. And, have to be careful being recorded. I'm not endorsing illicit activity. But if you guys need help with it, just look, right, there's the resources are there, just come talk to me, right? I think even on the AMU chemistry channel on YouTube, right? It's pretty much only me who posts there. So in case you guys don't have enough of me 3 days a week, right? There, I have some work through examples of past quizzes and exams on there too. That might be a good resource for you guys, whatever it might be, right? And if none of that works because you're sick of my voice, I don't blame you, right? There's plenty of other things I can help you out to find also, right? We added another tutor for this course also. So in case Laura's schedule and yours doesn't match up, then Joe's going to be sitting in here also, and he'll be working as a tutor for this course. Okay. So the resources are there. You guys just have to reach out, figure out, and let me know what it is, what I can do to help you out, or whatever it might be. Okay. Cool. All right. So let's finish this up real quick, and then we'll get into one of my favorite chapters. The last kind of idea that we wanted to work through here was about the standard molar enthalpy of formation. There'll be a slight typo here in just a second, I think, but I'll point it out to you guys. But anyway, again, if you go to the back of the book, there's these tables of appendices and all these kind of things that list a bunch of delta H's of formation. Now, these are going to be useful for us, like on the examples in class there, we do a reaction. I give you guys a delta H for that. Well, how in the world did I know what that delta H is? Or how in the world did the authors know what that is? Well, fortunately, there's a lot of chemists who have nothing better to do with their time, right, than to calculate and figure out what delta H's are for these reactions. And that's where we can tabulate that stuff at the back of the chapter there, okay? So some of the examples that you guys might need to, some of the examples that you guys will be working through, at the end of the chapter, you'll need to go look up those tables at the back there, okay? So if you see the delta H F of formation here, that little lowercase, right, that's the values that you're looking for, right? That subscript F there is the enthalpy of formation, okay? The difference is kind of stated up there in the blue, right? The enthalpies of formation are for a mole of the substance. So you'll see sometimes that they have like these fractional stoichiometric coefficients there. That's to make everything per mole of the compound that they're interested in. You guys catching me on that one? Right, so that's not how we would normally deal with stoichiometry, right? Stoichiometry is always going to be our whole integer values, where this is our balanced equation, but this makes 2 moles of liquid water, and we just want to report it per mole of liquid water, is what it is. So they just divide everything by 2. Okay, so just be careful with that. Does that change anything practically for you guys? No, right? It makes the math easier is what it really comes down to. Otherwise, you guys would have to go through and do that yourselves, and why do that extra work, right? So just pay attention to that is what it is. Yeah?
Why is there a degree symbol?
That just indicates standard state, right? It indicates the pressure that this is run at. Because as soon as you change pressure, then you would change delta H.
So it means standard pressure, not like constant pressure?
It means both. There's a standard pressure and we maintain that pressure.
Okay.
Yes. Ta-da, right? So there it is, right? So, well, a couple of, this slide just kind of shows a little bit of exceptions, I guess, to the rule. Right here at the bottom is probably the most important one. So the enthalpy of formation for any element in its standard state is going to be assumed to be 0, okay? So if we're going through a problem, which we'll do an example in just a second, and hydrogen is part of the problem, H2, right, then the enthalpy of formation for hydrogen is assumed to be 0. Okay, so the enthalpy of formation for any element in its standard state. So remember, we've got our 7 diatomic elements, right? Hydrogen, nitrogen, oxygen, right? Fluorine, chlorine, bromine, iodine.
Have no fear of cold fear.
There it is, right? So any of our elements in their standard state will have an enthalpy of formation of 0. Now be careful, because if you look in the back of the books, specifically something like carbon, there's different allotropes of carbon. There's carbon as graphite, there's carbon as diamond, there's carbon as these nanotubes, whatever, right? There's different forms of naturally occurring carbon, but only one is its standard state, and that's going to be graphite, okay? So you will see a value of carbon as a diamond and a delta H for that. That's not the standard state of carbon, okay? So you do have to pay attention to the state of the materials that are part of our equation. Hang on just a second, Rachel, right? So specifically here, right, there's the delta H of formation for bromine as a liquid is equal to 0, because that's the standard state of bromine, okay? In its elemental form, it's a liquid. It's different if we're talking about bromine as a gas or bromine as a solid, then it's not going to be delta H. Excuse me, then it's not going to be equal to 0. Okay? Yeah.
What about sulfur? Is sulfur, is that natural state S8? Or?
There's actually different forms of it, yeah. I think S8 is the most stable, but there's also S2, S4, and S6.
So would that be the standard state is S8?
Yeah.
Okay.
Yeah. That'd be a fair assumption to make. If there's anything oddball, I'd give you guys some information about that, right? These odd types of, let me put it this way, the odd elements that exist like that, then, I'd have to give you, I'm not gonna try and trick you, let me put it that way, right? I expect you guys to know the 7 diatomics, that those would be their elemental forms, right? But everything else, I'm not gonna trick you guys with that stuff. It's already tricky enough. Okay, so again, these problems just become, look up stuff, put together, and see if we can come up with an example. So here's where your typo is. I don't think it's Appendix J anymore. This was from a previous version of the textbook. I'd have to look it up, I'm sorry. If one of you guys have it, then we can let you know here. But I think it's like C or D or something like that, but it's in the back. But anyway, it'll look something like this, and you guys will see your delta H of formations off on one side there. And those are the values that you guys are gonna use when you're solving these types of problems, okay? And I'll show you, the next slide here, we have an example. Is this it? Yeah, okay, so it's appendix C has it, appendix C.
We don't need to memorize these, right?
I sure hope not.
Okay.
Yeah, me too.
Let's see, do I hate you guys? No. Okay, so no, you don't have to memorize these at all. Cool, so appendix C, when you guys are working with problems there. All right, so how in the world do we use these values? Well, it's that formula up there at the top. So the change in enthalpy is equal to the sum of the enthalpies for the products minus the sum of the enthalpies in the reactants, okay? It's not a big stretch here, okay, to think about if we're looking at the change in enthalpy. Remember, if you go back a couple slides, we were talking about making and breaking bonds, okay? You break bonds, it takes energy. You make bonds, it releases energy. So it's the same idea here. We're just taking the enthalpy for the products minus the enthalpy for the reactants. The one thing that we do have to pay attention to, as always, is our stoichiometry, though, right? Take a note that we have, right, the sum. Let me zoom in here real quick so I can point at stuff. Ooh, not a bit much. Right? So in our equation, right, we have our lowercase n, that's moles, right, our stoichiometry, okay? So pay attention to that when we're going through and solving these problems. Where do I find information about delta HF?
In the book.
It's in the book. Where do I find information about delta HF?
The book.
Got it? Right, so we have to have a bounded equation, and we have to have those values, and then we can solve these problems. It's gonna sound tricky. It's got delta H, now it's got a little degree symbol, it's got a lowercase f. How much more stuff can we cram around enthalpy, right? But that's all it really comes down to, is just looking up these values and paying attention, okay? Paying attention to your stoichiometry. So here's what I mean. So if we have a question that says calculate delta H for this equation here, okay? If we have a question that says calculate delta H for this equation here, first thing you need to do is make sure that it's balanced, okay? You guys can assume that I gave you a balanced equation in this case. Then the equation becomes, look up delta H for hydrogen cyanide, for hydrogen, for ammonia, and for methane, okay? Don't forget to bring your stoichiometry. Okay. So products, the sum of the products minus the reactants, right? Minus the sum of the reactants, I should say. Good? Yeah. So what does this 134 represent? The enthalpy of formation of HCl. Got it? Why is this 0 here?
H2 is a direct comment.
H2 is the standard state of that element. Got it? So 3 times 0. Not too bad. Where does the negative 46 come from? Standard state, or the enthalpy of formation for ammonia, and the negative 74 for methane. Pretty easy, right? Balance an equation, look up delta H's. Add up the products, subtract them from the sum of the reactants, right? Pay attention to the states, solid, liquids, and gases. Pay attention to the standard state if you have any elements in there, right? The enthalpies of formation are going to be equal to 0. Good? All right. Whew. You know what that means, right? End of chapter 5, finally. All right. No, chapter 6 gets into the fun stuff.
Well, I don't know.
You don't have to.
This is when we get to do the, like where we get to drop the electrons around an element.
Yeah, we'll get there.
Yay.
First we have to build an element, right? So the next 3 three chapters deal with how we can actually build an element. So just as a quick, or not build an element, build an atom, I should say. So as a quick aside, what we've been learning so far are the, once we have a molecule, what can we do with it? Can we precipitate it? Can we do a redox reaction? Can we burn it? Can we calculate some of the properties of it, when it reacts, these kind of things. But now we're going to take a step back and actually figure out what an atom is and how to build one of those. So chapter 6 is building an atom. We're going to go from chapter 6 into chapter 7 and 8 where we say, okay, once we have an atom, what are the properties of those atoms? And then chapter 8 is, okay, once we have those properties, now let's put them together and look at the molecules themselves and answer the question, why do they behave in the way that they do, right? How do they look? What shape do they have? Where are the electrons? Where are the atoms? All this kind of stuff. Because if you back up for literally just one slide, right? In the chapter 5, we were talking about making and breaking bonds in the products and the reactants. Well, how many bonds are there in between the hydrogen and that carbon in hydrogen cyanide? Well, we need to figure that out. How many bonds are there between the carbon and the nitrogen? Well, we need to figure that out. So that's what we're going to learn next, okay? We're going to build an atom, and then we're going to build molecules, and we're going to look at the properties of those, okay? So we're going to start out with a little bit of math in the first part of chapter 6, and then it's going to become very conceptual. So it's a swing in what we've been doing, okay? Chapter 5, very math heavy. Chapter 6, 7 and 8, not so much. And even 9, I should say. Okay. So, energy increases and the electromagnetic spectrum and all this kind of stuff. So the first thing to think about is that what we're going to be talking about is, or where we're going to build to is, where are the electrons living around the atoms? And we're going to have to construct the idea of orbitals, okay? And each orbital is going to have a certain energetic level associated with it. And we're going to be able to measure that relatively by looking at the amount of energy that's given off or released as we push an electron from one house to the other, from one orbital to the other. So we're going to talk about excitation or relaxation of electrons, and they're going to give off different wavelengths of light. Okay? So when we're dealing with wavelengths of light, we're going to be down in the nanometer range. Okay? And if we're in the visible spectrum, we're somewhere between, 400 and 700 is what it is. Right? So it's very interesting that here is our world, right? Our world exists in terms of what we can see in a very narrow range of electromagnetic radiation. But, as you guys I'm sure know at this point, right, the sun gives off nearly every wavelength of energy, right? We're getting bombarded by IR and UV and micro and X-rays and all this kind of stuff. We just can't see them. Why? Well, our eyes can't detect them, right? Yeah?
What if we gave ourselves an eye transplant from a mantis shrimp?
Well, I know there are certain animals that, can see infrared. Like I know some snakes can and things like that, right?
Birds can be often seen ultraviolet. The mantis shrimp has 16 cones in its eyes, which means you can probably see like a ridiculous number of colors.
That's super cool. But I wouldn't recommend giving yourself shrimp eyes. Because then you can't
Why
take
not?
because then you can't take the exam on Tuesday. So there you go. All right.
Michael has a point.
Anyway, so this is useful for us to recognize, and what we're going to figure out, and where we're going to get to, is that as we excite and relax certain atoms, they're going to give off distinctive bands of energy in the visible spectrum, and we can identify what elements exist in distant stars and things like that, right? So if you ever wondered, we found a new star that was X billion light years away or whatever it might be, and it has a high amount of iron in it. And we're like, well, how the hell do they know, right? It's because iron has a specific emission wavelength as the electrons are going in between the different places where they can exist around an iron. Exist around an iron atom, okay? Yeah, right? Well, not as soon as, right? They're continually formed. Now the question should be, why do they form iron, right? Yeah, but why iron?
They work their way up to, it's because of the mass. It's because of how the density is not heavy.
Okay, why not nickel though?
Well, because it's not the threshold.
What makes the threshold?
The universe.
Okay, right? But the question should be why iron of all things, right? Why not nickel or cobalt or zinc for all things, right? So there's something special about iron, but we'll get into that a little bit later. Right? But it's a good question. I'm not saying that, okay? So anyway, what's the relationship between wavelength and amplitude and frequency and all this kind of stuff here? Let me give you guys the equation here first, and then we can kind of, I'll give you guys the magic idea here. Ooh. Okay. So one formula to keep in mind is c, which represents the speed of light, is equal to lambda, the wavelength, times the frequency, okay? Now c is a constant. Well, I should put a
Why are we using
big.
C for so many things?
Hmm?
Why are we using C for so many things? In the last chapter, C was like,
That was capital C though.
no, the lowercase c in MCAT is like for,
Sure. And that's why we always have to specify the units and what exactly it is, right? That's why I always put C of water, right? I'm not saying the speed of light of water, that doesn't make sense, right? But you're right, we only have 26 letters in the alphabet, so what would you want to use instead?
One of the other
Star,
One of the other ones.
Star Wars.
Fair points, okay. But anyway, so speed of light, lowercase c, that's a constant. I give you guys that information on the formula sheet, right? But as you guys are working through the practice problems for this chapter, you guys are gonna probably just know this anyway, right? 2.99 or 3.0, right, times 10 to the 8th meters per second, right, is kind of the acceptable speed of light that we use. Wavelength and amplitude and frequency. Frequency is given in units of hertz. It's a per second, right? It's a well, if you think about frequency, it's if I sat here and snap my finger, right? How many snaps am I giving you guys per minute, right? Or per second? How frequently am I snapping my fingers? That's that
Snapping
idea.
a little less frequently than every 1 second, so probably around 1 point.
Sure. Okay, sounds great.
Starts counting.
Right? But the point is, right, when we're dealing with frequency, that's exactly what we think about. How frequently does something happen? All right? Amplitude is just the wavelength, or excuse me, the distance from the top to the bottom there, the crest to the peak of the name that I'm, wave, excuse me, I forgot the word wave, right? From the wave of the energy that we're dealing with, all right? And then wavelength is just the distance between the tops or the bottoms of the wave themselves. Now, here's what we have to think about, okay? The relationship between amplitude and frequency and wavelength and all that kind of stuff, right? And this is gonna be important, because as we deal with energy, how does an increase in energy change our wavelength? How does an increase in energy change our frequency?
Would it stretch it out?
Well, we'll get there, right? But this is what we're gonna have to deal with, because in just a couple of slides, we're gonna talk about, which has a higher wavelength, or which is a lower wavelength transition. And it's all related back to the energy associated with that, okay? So I'll give you guys my secret technique here, when we're dealing with energy, wavelength, and frequency. It's this, it's your pointer finger, okay? Not to be confused with your middle finger, or your ring finger, or your pinky. I want you guys to do me a favor, right? Come with me here for a second, hang on. Okay? So I want you guys to start drawing a wave for me. You guys ready? Go. Come on, do it. Everyone's got to do it, all right? We're drawing a wave. Nice and easy and relaxed, right? Now I want you guys to draw a much shorter wave. Which one took more energy? The one with a higher frequency and a shorter wavelength. You guys with me on that?
Yes.
Now if you do a nice relaxed wave, it doesn't take much energy, right? Low frequency, low energy. Okay? Good? Thank you, science pointer finger. Right? So if you guys ever have to think about that relation, that's literally all it is, right? High frequency is high energy, Low wavelength is high energy, okay? Good?
Low wavelength is high energy?
Short wavelength, yeah.
How is any of this determined?
How is what determined?
How did someone figure this out?
Well, we can measure wavelengths, right?
How?
Well, sure, we'll talk about it. We can measure energy, right? And if we know, if we have a relationship like this, right, we have a constant, then we have two variables, as long as we keep one of those constant, then we can figure out the other one, right? Okay. It's a good physics question. Good thing I'm not a physics professor.
How does the speed of, or how does light relate to this? Because isn't light both matter and?
Yeah, we'll talk about that idea in a little bit.
Well, RF goes the speed of light, right? Like, I mean,
What is RF?
radio frequencies.
Well, all of these travel the same speed, right?
Right,
Yeah.
so they're all going speed of light.
Yes, that's our assumption.
Okay,
Oh, okay, I follow.
that's why radio is more,
Right.
instant than television.
So this isn't too important. It's just kind of some background information here. Emission spectrum and thing like this, right? So what the next couple of slides, I'm gonna build you guys up towards the idea of the model of an electron, right? So there are some important ideas underneath there. The idea of energy and how that changes the emission spectrum and this kind of thing. What the Planck's theory here kind of comes down to is at a higher temperature, shorter wavelengths, and classical physics couldn't explain this, and so basically they started to do some experiments and they're like, wait a minute, nothing's behaving like we expect it to. Okay, that's kind of what the idea is here, right? We expected the atoms to behave in the way that we can see the universe, right? But what the realization was, or what we know now, is that when you're dealing with really, really, really small things like electrons and protons and neutrons, classical physics falls apart. Okay, and that's why we have to develop quantum physics, right? So we have to develop a whole new set of ideas and principles and equations to deal with this kind of stuff, right? And this is kind of one of the first experiments where they all started to scratch their heads and say, I can't explain this. So what in the world is going on? So here's the best explanation I can ever come up with, or I can visualize the idea between classical and quantum physics, right? So in classical theory, there's no restriction on the energy emitted by atoms, okay? But that didn't fit the data. So I said, okay, well, the atoms emit energy in specific packets, they're quantized, okay? There's discrete packets of energy, okay? They notice that each packet has a minimum energy, and the energy of that quantum is equal to h, which is a constant, times the frequency there of the radiation, okay? So that's another equation for you guys to know there, E equals hv, Planck's constant, times the frequency.
Is this gonna be out of the
Yep. But if we take a look at frequency, right? We know that the speed of light is equal to lambda, or wavelength, times frequency. So oftentimes we can rewrite this equation as Planck's constant over wavelength, right? If we just solve for frequency and just plug that back in there, okay?
Wait, what you're saying, the HC over thingamabobber?
I'm saying if you rearrange this for frequency, right, you divide by lambda, right? Then frequency is equal to C over lambda, and you just plug that in here, right? If I take and I rearrange this equation, I solve for frequency, it's equal to lambda over C. And then I just plug that into that equation there, right?
Oh, okay, follow.
Okay.
Yeah,
Good? Why is this important? Well, now we have a way to relate energy to the speed of light and wavelength. And all we need is that constant in there, okay? So good, now we can relate energy that we calculate to wavelength. If we can measure the wavelength of light, then we can relate that back to the energy, because the speed of light is a constant, Planck's constant is a constant, right? So we have a very simple way of relating energy and wavelength. You guys with me on this so far? And that's where we're going to spend most of our time at the beginning of chapter 6, is this idea of the relationship between energy and wavelength. Okay? Now, just as a quick this and that, how does this relate to what we're going to be talking about? Classical physics is a ramp. Okay? So if you imagine yourself walking up a ramp, there is a continuous increase in energy for whatever system we're looking at. Okay? A ramp is a nice smooth surface to get us from the bottom to the top. You can stop at any point in between there. Okay? Quantum physics basically says now we're on a set of stairs. Now what's the difference when you're on stairs versus on a ramp?
It's incremental.
It's incremental. Can you stop at half a stair?
If you're really determined.
Well, you're going to fall down, right? And that's another idea, okay? We're going to talk about taking a step up or a step down, right? Stopping at a specific set of stairs, going up takes energy. Is it easy to fall down the stairs?
Yes.
Yeah. Well, I'm not saying it's not painful, right? But you can fall down the stairs, but it takes energy to go up. And you release energy when you go down. That's going to be important.
So it's like
Okay.
all or nothing.
Not necessarily.
So would going down be like fission?
No. We're dealing with electrons, not that's nuclear chemistry.
Okay.
Yeah.
So like when you have like the electrons, right? So you need like a full electron shell.
You don't need a full electron shell. We'll get into that. It's a good. I can see where he's trying to get with this, but hang on. I have to first build you the simplest of atoms: one proton, one electron. Then we get into the more complex stuff.
Hydrogen.
That's it, right? So the idea is this: when you are adding when you're adding energy into an atom, it's going to go to, or one place it's going to go to is where the electrons are. And if you give an electron enough energy, it's going to take a step up. It's going to be a discrete step. It can't stop at a halfway point, okay? And we can measure that then. We can measure the energy that's emitted or absorbed. If you're taking a step up, it takes energy. If you take a step down, it releases energy, okay? Now we're going to have to pay attention to whether we're dealing with the energy of the electron, the energy of the atom, or the energy that we add into the atom. And so when you go and read through the book, they're going to start to relate the energy of the photon versus the energy of the atom. You can think of it like what we just dealt with in chapter 5, the system and the surroundings. If you guys are heating a pot of water, right, you have to put it on the stove. So the energy comes from the stove into the water, okay? The water increases in energy. What happens to the stove, right? It decreases. What you put in is what you get out there, right? Same idea here. But we do have to pay attention to whether we're emitting or absorbing energy and whether we're going upstairs or downstairs. Okay, upstairs takes energy, downstairs releases energy.
What if we mattress surf the stairs?
Well, then we're in physics class, right? All right. So I think this is an experiment that we used to kind of do in Gen Chem Lab. You guys might do it. It's actually kind of fun. You get to burn things. I know you guys always appreciate that.
Duncan
But
Thomas banned me from any open flame experiment.
I don't blame him on that one. Right? But anyway, so if we take a certain metal element, right, and we heat it up really hot, aka stick it in a flame, we can start to see distinct wavelengths of light get emitted from it. But you guys already knew this, right?
Yeah.
How did you guys know this?
Set copper on fire and it turned green.
What else?
Make the metal hot and it turns red.
So be careful with that, right? We're talking about the emission of light, not just adding energy to a metal block.
So now,
Where do you guys see pretty colors
Television!
exploding in the sky?
Fireworks.
Fireworks. Where do the different colors of fireworks come from?
Chemical compounds.
They put some metals in there, right? They put some gunpowder to add some energy, and they put different metal salts, right? If you put nickel in there, it gives you a color. You put zinc, it put a different color. You put aluminum, you put copper, right? That's really all it is,
Just make really pretty colors.
right? So I used to rent a room from someone who used to make his own fireworks. So I was always had interesting discussions with him about the colors that he put in. It's super fast. I was scared, right? Because it's like, oh, I'm gonna go pack some gunpowder, like you're making a bomb, right? And it was out in the middle of nowhere in the woods of Tennessee, right? So the optics, right? So gunpowder supply to Tennessee is what it is. Okay, anyway, right?
Sounds like a good time.
But in the lab, literally all you need is a Bunsen burner. You get the different metal salts. You burn it, it makes pretty colors, right? It's gonna change the color of the flame. And with this little handheld spectrometer, you can actually pick out the individual wavelengths. So if you burn nickel, you're gonna see distinct nickel pattern, right? If you burn mercury, you're gonna see a distinct mercury pattern, right? And you guys already knew this too, because I don't think we have them anymore, right? But we used to use mercury as part of our in our light bulbs, right?
You mean it's early something like that?
No, we're talking about these.
It's like the fluorescence.
Yep.
Yeah.
All right. So, how did this all come together? Where did we all try to put this together? So, Niels Bohr came to in 1915, essentially 1930, excuse me. Right. So not that long ago, only about 100 years since we started to figure this out. And we can find that the orbits of the electrons are in distinct steps around the nucleus. Okay? And this is important because we can actually measure that energy with a constant, and if we know what the steps are. So we have N is step 1, step 2, step 3, step 4, step 5. So if you imagine yourself going upstairs, each one of those N's represents a specific step, where 2 is bigger than 1, 3 is bigger than 2, etc., etc. Okay? N just represents an integer value. Yeah.
So, you're saying that that's like the orbit around the atom. So is a lower number the outer shell, whereas the
No, the lower the number is the closer the nucleus, right?
Okay, so do different atoms have like a different maximum N
Yes.
for their outer shell?
Yes.
Okay.
Because like hydrogen only has the one. Right?
Correct.
And then the like lithium would have 2.
Sort of. We'll talk about this in a second. Yeah. You have a question, Amy?
Yeah, E is just how much energy.
The energy of that step, right? Right, the energy of this step here is what we're calculating. And then we can just compare the two energies at different levels, right? Cool, all right. So that is it for today. All right, that's it for today. I will see you guys on Monday. We'll continue working through chapter 6. And then we've got our exam next week, all right? Let me go.